Hello everybody, it's Francesco Leoni here, and today I'm going to present you um, a preliminary calibration of a numerical model for the hybrid metal extrusion and bonding process. So the purpose of this work is to develop a numerical model for the hybrid metal extrusion and bonding process in order to predict the mechanical properties evolution of the material subsequent to this novel joining technique. In this preliminary part, temperature evolution was considered to calibrate the model. I will start with a background on the hybrid process to make you more familiar with this welding technique. I will explain you how the tool works. I will show you the experiment setup, the welding summary, simulation setup, and finally I will give you some results, and I will talk about some conclusions that can be made after this work. As I said before, the hybrid metal extrusion and bonding process is a novel welding technique that has been developed in Trondheim, Norway. The method utilizes continuous extrusion as a technique to enable filler metal addition. In aluminum-aluminum butt welding, for example, the bonding is reached through a combination of oxide dispersion, shear deformation, surface expansion, and pressure. Here you can see a picture of the tool that is joining two plates of aluminum, and you can see the main parts of the tool. With this slide, I want to show you the potential of this technique. Since, as you can see here, many different scenarios were tried, and good results were obtained in joining different metals and using different setups. And you can find some works in the literature which give you also some numbers on the efficiency of the joint. This slide, you can see an example of a cross-section of a butt weld obtained with the HYB process. As you can see, it can be recognized the filler material and the base material. This is an aluminum butt weld, so you can see how the filler material is mixed in the groove, and this is made by the rotation of the pin, which passes through along the welding direction and rotates. So it's similar to the principle of friction stir welding, but here we have a gap between the plates, which is filled by the filler material. And the table here shows also a benchmarking of this process against the gas metal arc and friction stir welding based on a comparison of tensile tests obtained for 4 millimeters thick aluminum butt welds. And as you can see here, the process is capable to compete with those widely used technologies. Now I'm going to show you how the tool works, and I will try to explain you the main features that this tool presents in order to make you familiar with this technology. So how the tool works? Here you can see the main parts of the tool and the most important ones, which are the pin, the stationary house, and the filler material that goes inside the housing, and by friction between the rotating walls of the extrusion chamber, a continuous extrusion of the material into the rotating dies of the pin is possible, and makes the material flow inside the groove, which is filled, and the joining of material is then reached. Uh, Probably not all of you are familiar with continuous extrusion or extrusion processes in general. So here you can see the different way of extruding material, and you can see the continuous extrusion, which is the principle behind this process, which presents the abutment, as in our case, the rotating pin, which is a wheel usually in the continuous extrusion process, and a filler material, which is a filler wire. And so you can see how this technique is used in our case in order to fill the, the gap between the plates that have to be joined. This is an animation that maybe clarify you which are the parts that rotate and which are stationary. Of course, all the tool moves along the welding. So I wish this is helpful to make you understand better the process, and we can go ahead with the experiments set up that have been carried out. So the experiment consisted in welding of aluminum alloy 6082 received in T6 condition, and the plates were 4 millimeters thick, and what was measured was the power consumed by the machine, and it was used a couple of thermocouples placed 3 and 4 millimeters far from the groove surface wall in order to obtain the temperature evolution in those points and to compare those with the simulation. As I said, two thermocouples were used. One was placed 110 millimeters far from the start position of the weld, and it was 4 millimeters far from the groove wall surface on the advancing side. The second one was 20 millimeters ahead of the other one, and it was 3 millimeters far from the groove wall surface on the advancing side too. And so this is how the temperature was measured. Once the weld was run, we obtained the temperature evolution, and as you can see here on the left, of course, 3 millimeters far from the groove surface wall, the temperature is higher since it's closer to the heat source, and moreover, the hardness was measured along a cross section of the weld in order to determine how the temperature field affected the strength of the aluminum alloy. Let's talk now about the weld sim code. So weld sim is basically a transient, nonlinear, three-dimensional, finite element computer code for both heat transfer and solid mechanics analysis. The software has been developed with a particle size distribution model inside that is capable to predict the microstructure evolution subsequent to a thermal history, which keep track of the nucleation, growth, coarsening, dissolution, and so it is capable to predict the strength evolution of the material. The particle size distribution model consists in the three parts here presented. Basically, a nucleation law which predicts the number of stable nuclei that form at each time step, a rate law which calculates either the dissolution and the growth rate of each discrete particle size class, and a continuity equation which keeps a record of the amount of solute being tied up as precipitate. Then we assume that the yield strength at room temperature can be written as the sum of those four contributions. The first one is the particle strengthening. The second is strengthening from Wiener-Preston zones. The third one is the contribution from alloying elements in solid solution, and sigma I that is an intrinsic strength which is 10 megapascal for aluminum. The model is thus able to predict the evolution of yield strength and hardness of the material subsequent to the welding operation. Now let's pass to the simulation setup. So basically, it was necessary to model the geometry, and this was done in Patran, which is a software that permits the creation of a neutral file, which can be used as input in the Welsim code. And since Welsim needs the um, nodes coordinates and the boundary IDs um, to um, to set the boundary conditions between the plates, thermal boundary conditions and mechanical boundary conditions. 6 domains were defined as presented here, and the heat sources were placed, as you can see, in this part of the plates that were to be joined. So the thermal boundary condition are presented here in the table, and the heat source model used was a Goldak heat source model, which is a double ellipsoidal heat source, and the parameters used are here shown in the table below. So let's go ahead. An iterative approach was used in order to find out the actual heat input to give to the simulation to get the best fit with the experiments in the thermal field, and so to get the best possible prediction in the strength of the material. Let's see some of the results. So here you can see an example of the plates during welding in the simulation. The temperature field evolves like this, and once the simulation is done, it is possible to extract the thermal field from the points that we set, the pre-processing part. So by means of an interaction between Welsim and MATLAB, it was possible to run several simulations and make it possible to find out which was the actual power input to use in order to obtain the same thermal field as in the experiments, and so to obtain the best possible prediction in the microstructure evolution. The best fit input values were then identified, and as you can see here on the left, a good agreement was reached, and on the right you can see how the hardness prediction of the model is similar to what is measured in the experiments, but further developments will be done in order to obtain a better match between experiments and simulation. Let's give some conclusions. So, in conclusion, um, with this study, a good agreement between experiments and simulations was reached, and what was found is that only about 30% of the total power involved in the process is absorbed by the workpiece. The rest is absorbed by the plastic deformation work of the extruded material, by friction between rotating and stationary parts of the tool, and by heat dissipation to the environment. The heat efficiency of this process is thus very low compared to other solid-state joining processes such as friction stir welding, and also compared to other fusion welding techniques where the heat efficiency is typically 60–80%. However, the process here presents some unique aspects that make this heat efficiency not as relevant as in other traditional weldings. Um, the model will be further improved and used to predict the strength evolution of the material subsequent to high bond process in order to make a better optimization of the process. And thank you for your attention, and if you have any questions, don't hesitate to contact me by email, as you can see here, and so goodbye.